We're going to continue in section 8.3.2, but what we're going to look at now is finding all of the roots of a polynomial, and we're going to use some of those theorems to help us. So finding all of the roots just means finding all of the x-intercepts. So the first one's easy because it's a quadratic. So we have different strategies that we learned at the beginning of the year, and you learned in Algebra 1, to solve a quadratic by using quadratic formula, completing the square, factoring, taking the square root, and then graphing. So I'm going to factor to solve this, and I know everyone uses a different factoring method. I like the box. So I put the first term in the first box and the last term in the last box. And so I look at the product of the diagonal, and it's negative 10x squared, which means that the other diagonal also has to have a product of negative 10x squared, but it has to add to negative 9x. So that would mean that it would be negative 10x and positive x. And then you just come up with the edges by finding the GCF of each row and column. So this has to be 2x and x. So x times 1 is x, 2x times negative 5 is negative 10x, and 1 times negative 5 is negative 5. So the factors of this polynomial would be 2x plus 1 and x minus 5, but the roots or x-intercepts would be x equals negative 1/2 and x equals 5. All right, looking at this next one. So we have a cubic here. And so what we want to do is, again, we want to try to find all of the roots of this polynomial. So the first thing that you want to look at, again, is if you can factor or anything like that. So this one you could actually do factor by grouping. So what we would do is figure out, looking at those first two terms, what can you take out of both of them? We could take out an x squared. So if we do that, then we would get an x plus 1. And from the second two terms, you can take out a negative 7. So you would also get an x plus 1. And so your factors of this polynomial would be x plus 1, and then the other factor would be x squared minus 7. And then to solve it, you would just set them equal to 0, and that's how you would be able to find your roots. So your x-intercepts or roots would be x equals negative 1 and also x equals plus or minus root 7. So both of these were pretty simple because we had strategies to solve them, but it keeps on getting a little bit more complicated. So looking at this one, we actually can't factor by grouping because we won't have the same type of groups. So this is where we go to the rational root theorem. So that tells us that to narrow down the possible factors, you take the factors of the constant term and divide it by the factors of the leading coefficient. So our possible factors are going to be plus or minus 1 and 5. So those are the possible factors of the constant, and then we divide by the factors of the leading coefficient, which would be 1. Okay, so from there, we then have to write them out. So it would just be 1 and 5, and then we need to test them. So what that means is we want to plug it in for x, and if we get 0, then that means it would be an x-intercept because y would have to equal 0. But another thing we can do is actually divide by factors. And if we divide and we get no remainder, then that would work as well. So when you're testing these numbers, in my opinion, it's very easy and much quicker to use synthetic division. So I'm going to go ahead and start testing with 1, okay? Just because it's the first one that we should test. So I'm going to go ahead and write out the coefficients. So we have 1, 3, 1, negative 5. So when we do that, we then would write our 1 as our 1 would be the multiplier, and then we're going to go ahead and start. So I bring down the 1 and we get 1. 1 times 1 is 1. 3 plus 1 is 4. 1 times 4 is 4. 1 plus 4 is 5. 1 times 5 is 5, and we get 0. So what we just did is we found our first root. And what's really neat about that is once you end up with only 3 numbers, you then would turn that into a quadratic, and then you can solve the quadratic. So your idea is to get it down to be 3 numbers, which we did. So we would do x squared plus 4x plus 5, and I'm going to go ahead now and solve that quadratic. So I already know that the factors of this polynomial are going to be x minus 1 because it was x equals 1, and the other factor would be x squared plus 4x plus 5. Some of you might be thinking, well, let's factor that and get it. However, I could already tell that this is going to have imaginary solutions, so we don't want to write the factors in terms of imaginary numbers, so you would just leave it as a quadratic. So I'm going to go ahead and solve this using the quadratic formula. So x equals negative b plus or minus the square root b squared minus 4ac all over 2. So this would be x equals negative 4 plus or minus 16 minus 20, which would be negative 4 all over 2. So this turns into negative 4 plus or minus 2i over 2, which would then turn into negative 2 plus or minus I. Okay, so then that means I'm going to put it up here that our zeros, or I should say roots of this polynomial, are going to be x equals 1 and x equals negative 2 plus or minus I. And that makes sense that there are 3 because it's a third degree polynomial. Remember, negative 2 plus I is 1 and negative 2 minus I is another. All right, we have another one here. So we have a 4th degree polynomial, which means we know that we are going to have 4 solutions or 4 zeros. So it doesn't look like we can use factoring on this one. So we're going to go ahead and start testing the roots. So remember, step 1 is to find the possible factors of the constant term. So that would be plus or minus 1, 2, 3, 6, divided by plus or minus factors of the leading coefficient. So the 1 really doesn't matter. So let's go ahead and start testing. So I have 1, negative 1, negative 5, 3, and 6. And again, I'm going to just start with 1. So I bring down the 1, and then 1 times 1 is 1. Negative 1 plus 1 is 0. 0 times 1 is 0. And then we get negative 5. 1 times negative 5 is negative 5. 3 minus 5 is negative 2. 1 times negative 2 is negative 2. 6 minus 2 is 4, which means we did not get a remainder of 0, which means that this one is not a factor. So we must continue. So now let's go ahead and test negative 1. So we have 1, negative 5, 3, and 6. And we're going to go ahead and test negative 1. So we bring down the 1. Negative 1 times 1 is negative 1. Negative 1 and negative 1 is negative 2. Negative 1 times negative 2 is 2. Negative 5 plus 2 is negative 3. Negative 1 times negative 3 is 3. 3 plus 3 is 6. Negative 1 times 6 is 6, or negative 6, and we get 0. Okay, so that means that x equals negative 1 is a root, but we still have 3 others. So in the last problem, because it was only a third degree, once we got it down to 3, which is right here, we got it down to 3, we were able to turn it into a quadratic, but we haven't quite done that. So instead of retesting another number, we can actually just continue with these 4 numbers. So I'm going to go ahead and test another number. So we tried 1, negative 1. So I'm going to go ahead and test 2. So notice that, again, I didn't write the whole thing out. Once you find something that works, you can just go ahead and use that row. So I pull down the 1. 1 times 2 is 2. Negative 2 plus 2 is 0. 2 times 0 is 0. Negative 3 plus 0 is negative 3. Negative 3 times 2 is negative 6. And once again, we got another factor. So at this point, we know that the roots, I'm going to write it up here. The roots are x equals negative 1 and 2, and we're missing 2 other ones. But what we could do now is turn this into a quadratic. So the quadratic would be x squared plus 0x minus 3, or just x squared minus 3 equals 0. So x squared equals 3. So x equals plus or minus root 3, which counts as 2 separate roots. So I'm going to go ahead and add that. So now we have 4 solutions. And our factors of this we would write as x plus 1, x minus 2, and then we would leave that in terms of x squared minus 3. Okay, so we want that number. I think you guys will notice a pattern that we want the factors to be nice, so we don't want any roots or any imaginary numbers. Okay, last one. This is a big one. So once again, the way it looks, we can't really factor by grouping or anything, so we'll do exactly what we did on the last one. So step 1 is to write the possible factors. So the possible factors would be plus or minus 1, 2, 3, and 6. So those are the factors of the constant term. And then we want to divide by the factors of the leading coefficient, which would be 1, 2, 3, and 6. So when you write out all the possible factors, the other ones, 1 was in the denominator, so it didn't affect it. But in this case, we would have 1 over 1, which is 1. We could have 1/2. We could have 1/3. We could have 1/6. Then we go to 2. We could have 2 over 1, which is 2. 2 over 2, which is 1. We could have 2/3. We could have 2/6, which is 1/3. Then we could have 3. We could have 3 over 1, or 3 over 2. We could have 3 over 3, which is 1, and 3 over 6, which is 1/2. Then we could have 6. 6 over 2 is 3, 6 over 3 is 2, and 6 over 6 is 1. So we have a lot of factors to test, and I know some people may be thinking, like, this is crazy, but if we didn't have the rational root theorem, we would have an infinite amount of numbers to test. So at least this narrows it down. So we're going to go ahead and start testing numbers. So we'll start with like a 1. I usually start with a 1 to get started. So I write out my coefficients. So 6, 7, negative 36, negative 7, and 6. And I start with 1. And we do this process. So negative 36 and 13 would be 23. Then we get 23. Negative 7 and 23 would be 16. And then 1 times 16 is 16, and that doesn't work. It doesn't matter, we could already tell. So then we try another one. So we have 6, 7, negative 36, negative 7, and 6. And then we're going to go ahead and test another one. So I'll test like 2. So you will probably realize that this is not a fun process. It's probably one of the least favorite topics, but it's important. So we bring down the 6. 6 times 2 is 12. 12 plus 7 is 19. 19 times 2 is 38. Negative 36 plus 38 is 2. 2 times 2 is 4. Negative 7 plus 4 is negative 3. This looks good, and we get negative 6. All right, so once again, we have 4 terms. So unless that looks like it could factor by group, which it doesn't, we have to keep going. So I'm going to go ahead up here. So far we know that the roots, we know one of them is x equals 2, but we have to keep going. So let's try another one. So I'm going to use those 4 terms and try like 3. because I know those 4 is what we got. So we pull it down, we get 6, we get 18, 37, and I can kind of already tell that this is not going to work, but we can keep going. Yeah, so this is not going to work. So then we will pull those numbers again. Okay, let's go ahead and test -3. So we pull down the 6. -3 times 6 is 18. 18. Oh, -18. And then 19 minus 18 is 1. Then we get -3. 2 minus 3 is -1. -1 and -3 is 3. Yay, we got it. Okay, so another root is x equals -3. And now we have it down to 3 terms, so we can turn that into a quadratic. And then from there, we can see if it factors. If not, we can try the quadratic formula. This does look like it's going to factor. So we can create the box. We get 6x squared, -1. So the product of the diagonal is -6x squared, which means this diagonal also has to have that same product, but it has to add to x. So it would be 3x and -2x. So this would be 2x, 3x, 1, and -1. So our factors of this polynomial are going to be 2x plus 1, 3x minus 1, x minus 2, and x plus 3. But our roots will be x equals 2, x equals -3, x equals -1/2, and x equals +1/3. So we can see it's kind of a tedious process, but you do need to know how to do it. So I would watch and rewatch the video if needed.